Okay, can you all see now?
Yes.
Yep.
Full screen. Okay. All right. Well, welcome. We have joint meeting tonight again. Central Texas Consultants Network and Live Members group. So we are the Central Texas Consultant Network, and we promote the development of members' careers through professional and social networking, including publicizing member skills and sharing potential professional opportunities, and support the IEEE Central Texas section, which we are part of. And the Central Texas section, of course, is the local operating unit of IEEE. As well, those of you that are IEEE members know, we are a very large organization with 420,000 or more members in more than 160 countries. We have about 200 journals, transactions, and magazines, publications, and 30 or more than 1,300 annual conferences. This is our leadership team for this year. I am Luis Basto. I'm the chair. Jody Everett is the vice chair and treasurer. Bill Martino is the secretary. Kai here is the member at large. I think all of us are here right now. Sergio, I don't think I see him, but he's another member at large. We do have a couple of open positions right now, program chair and webmaster, if anyone's interested or knows someone who might be interested. And this is our website, which also is published in our monthly newsletter on the webpage. Well, with that, I will transfer the power to
Okay.
Kai.
Yeah. Okay. All right. So this is the March 16 joint meeting. This is our member of the group, the live member. I'm the chair. Tom Green is the vice chair. He's in Illinois.
Talk to the HEB. And with Michael.
Here.
Yeah, with Michael, I understand, yeah.
Well, okay. They did still.
Please mute your speaker, please. Bill is he's here, is our treasurer. Clyde Spingen is our secretary. I'm also the program manager. And John Purvis is our webmaster. So for this year's plan, we need your input on topic, speakers, and you as our future speakers. And the topic we interested are technology mostly, 5G, IoT, AI, smart city, smart home. Also want to know more about finance, hobby, travel, education. And we want to hear your story and your contribution. And we like to hear more about health and aging topics. We're also interested in history, some historic event, in how to develop certain formula and some major event that open up our eyes. So forecast for next few months, April, we have a gentleman to talk about software-defined radio. And in May, with Tom Altman talk about the general energy technology update on for this year. On the June, and we have a ex-Motorola. Terry is going to talk about vintage car restoration. So it's quite an interesting topic. For tonight, the title of the talk is Roll Ribbon, High Power, High Capacity Lithium-ion Batteries. And Joel Sandhal is our speaker. He's the president and CEO of this company. He has a long bio. I just sum it up. He's been doing consulting work to some leading worldwide battery company manufacturers. And he started and sold 4 startups. and one was sold to Motorola, our old company. And he holds 8 patents and also additional pending patents. So I'm not going to go, Joe's going to talk about this whole thing. Just want to highlight that it's a $45 billion industry. It's still based on the old design, old technology. And Joe's company is introducing a new technology that will address the key form, scalability, and some other issues. And Joe, you have the floor. So I'll take this off, and you can share your screen.
Okay.
So Kai, are you recording the session?
Yes.
Okay. Everybody see it there all right?
Not quite yet.
No. There you go.
Yes.
Okay, now you got it? All right. Okay. So anyway, Roll Ribbon, name of the company, and it's also the name of the technology. It's a trademarked product. It's patented, but it's we're promoting it as the new standard for high power, high capacity lithium ion batteries. And so we'll walk you through kind of how we got here, a little of the history. Basically, lithium ion cells, battery cells, the cell is equal to an electrochemical formulation plus a cell package. So they're, in some respects, two distinct different things. Currently, and historically, for decades now, there have been 3 principal cell package types: cylindrical, pouch, and prismatic, into which all kinds of lithium ion chemistries as well as other chemistries go into those basic packages. And then rolled ribbon represents then a new cell package, again, independent of the electrochemistry. So if you look at it, again, cell equals the chemical formulation, and then you have a package type. So why would you want a new cell package? Now, the problem is the current cell packages are designed for low power, low capacity applications. They grew up in an age when, the first lithium ion cells you saw were applied to things like laptops and cell phones and whatnot. And lithium ion, it actually has been around since the 1970s, when they were first born. They didn't start seeing widespread use until about 20 years ago. And 20 years ago, it'd be rare to find a lithium ion. Those of you who remember, that was pretty much the age of nickel metal hydride. And then lithium ion started creeping in. And 15 years ago, you found that there was a pretty good proliferation of them, but it was all consumer products. So that's all low power, low capacity. It's your cell phone, small batteries, stick it in your pocket. It's consumer electronics. They started putting them in video cameras and small products. And so those cell packages worked out fine. They were all relatively low power, low capacity. The problem with those packages, they don't scale up. When you need high power and high capacity requirements, there's some dynamics in play. The physics don't work for you. They work against you. And so as you scale them up, the performance decreases and then the cost of the product actually increases. You end up with impedance and thermal issues that emerge, and they're difficult or impossible to solve depending upon what kind of power delivery you need in your application. And heat is the arch enemy of electrochemistry. It's the #1 thing that causes electrochemistry to degrade and depreciate over time. And the solution was, and rolled ribbon was actually specifically invented. The guy who invented it is a guy named Tom Kahn, lifelong electrochemist, worked for Argonne National Labs his entire career. And they recognized early on that lithium ion had a lot of potential to serve things more than cell phones and laptops and digital cameras and things like that, that it could serve much larger products that would require larger batteries, higher capacity, and more power. But due to the scalability issues, so how do you solve that problem? And so that's really what Tom Kahn set about to do, was to solve the problem of how do you come up with a different way of solving or packaging a lithium ion cell so that you don't end up with those scalability issues. And he came up with rolled ribbon. What it does, it reduces the impedance in the cell, which is better for power delivery, high power, hence provides unparalleled thermal performance orders of magnitude better than anything out there even today. And it's infinitely scalable. There's no cost penalty. So you can start with a given capacity cell, move up the food chain to a higher capacity or even higher powers, and you don't pay a price in terms of performance or cost to scale it. And the method that he came up with was compatible with all the present lithium-ion electrochemical formulations. So at the end of the day, every lithium-ion electrochemical, again, remember, a cell is electrochemistry plus a package. Well, every lithium-ion electrochemical formulation, the chemistry, the soup inside the can, performs better in a roll-ribbon package. And so we'll kind of get into that. But why does that matter? Well, why do you really matter? What most people aren't aware of. So again, if you go back 15 plus years ago, there are only a handful of lithium-ion cells out there used for anything. If you go back even a few years past that, as recent as 2013. So if you look at this chart here, and I don't know if you can see my cursor here, but so if you look at 2013 here, if you divide this, here's your consumer electronics. Those are low power, low capacity. And then these are applications, industrial, grid, transportation. They're all high power and high capacity. And this is the size of the market in dollars. This is in billions. As recent as 2013, which is only some years ago, the market for lithium-ion cells was a little less than 15 billion, 10 of which was for low power, low capacity. So it was the cell phones, the laptops, even 7 years ago. But then you started to see a significant percentage of high power, which are the three other colors you see stacked up here. Well, if you look at it, here we are today in 20, the market for 20, the low power, low capacity market is still 10 billion. Now, there are more cells out there because the cost has come down, but it's a flat market. It's still $10 billion today, like it was $10 billion in 2013. But all the growth that you see is in high power, high capacity. And in fact, as far as the eye can see in anybody's forecast, they expect by 2023 that the lithium ion market in total will be $80 billion, of which $70 billion will be high power, high capacity. And you'll still only see $10 billion in low power, low capacity. So the markets in high power, high capacity, that's the problem to solve because that's where the money's at. And if you look at the high power, high capacity, so growing from 2020, you're talking about going from $43 billion out of 52 total is high power, high capacity. And by 2023, you're looking at $70 billion, or 80 out of $80 billion, $70 billion of that is high power, high capacity. So that's the market that matters. The low power, got that solved. High power, not so much. So why is it a scalability problem? Well, if you look at the structure of the current cell packages, this is kind of a breakout here, and you can kind of see how they're put together. So if you take a cylindrical cell, and those were actually the earliest cells that were made. That's the oldest, that dates back 60 some odd years, actually 70 some years. They're all made with what's called a wound tabbed structure. Pouch cells are usually a soft case cell. They tend to be flat. More recent laptops and things tend to be pouches, and they're buried inside. Like if you get a Apple Mac and a lot of their cell phones today that don't have replaceable batteries, they tend to have pouch cells inside them, more compact. There are two ways they can be made. They can be what's called wound tabbed, or they can be stacked tabbed. And then you take the prismatic cells. Those are the ones you can sort of think of those as being rectangular like the pouches. They tend to be a little thicker, and they tend to have a hard case on them, usually aluminum or steel or something of that order. And again, they can be constructed like pouches as wound tab cells or stacked tab. But what does that mean? A wound tab cell, what you do is you take an electrode here, and you take it, and it has some height to it, and it has some length to it, and then you wind it up into a roll, as you can see down here. And basically, you get capacity based on the number of square inches of electrode area that you have. And you wind it up, and so the bigger the roll, the greater the capacity, more square inches of electrode you have, the more capacity you have. And then there's a tab that's welded onto that electrode here. And so the electrode is actually a foil and then it's coated with electrochemistry. And the way the cell works is they weld a tab onto the end here, and that welded tab is welded to that sheet, electrode sheet there. And then the tab is then welded. And so if we go back to, it gets welded then to the terminal on a can here. Or if you wind it up, it could be welded. This could be the welded tab here or welded to the terminals there. Now, what happens when we say it's not scalable? So I have a small cell here, and like the original laptops were all 18650s. That's actually where 18650s came from. They wanted a commoditized cell, and that was a convenient cell size that you could universally apply to all kinds of laptops. And so that's where 18650s came from. And so you ended up with a certain amount of material there that gave you capacity for the cell. Electrochemistry gave you voltage, and you move on. Well, what if I want more capacity? If I want to sell more capacity, I need more square inches. So what you'd have to do is you would tend to make the electrode longer, and when you wind it up, you'd end up with a greater diameter here, because now you have more material wound there. And that's where cells like 26650s came from. But what happens is all the heat and all the electrons from the cell, where you get your current, they have to travel the length of this electrode and come out the tab. So all the heat and everything runs down this long, tortuous path of electrode. All the thermal, which is in red here, and all of the electrical runs here. And if I make the cell bigger, the more capacity I need, I have to extend the length of this cell here. And when I do that, I now have more impedance, I have more material, more resistance, and I have more thermal resistance because the path is longer. And so the cell becomes inefficient. And in fact, what you see in thermal, this is the model here from NREL. You can see that the cell gets, you have uneven heating. It gets very hot in the middle. In here, the tab is on the outside, so it's cooler. It's closer to where the heat escapes. But this travels a longer path, so the heat becomes pent up and built up. And when you have gradients in a cell, you have uneven wear. The cell will wear out faster when you do that. And so the problem with the structure in a wound cell is you have more to wind when you want more capacity. And then when you get power delivered faster, if you want high current rates coming out of there, as we all know, that's I squared R. So you add a little resistance in the path, but that resistance, and as the current increases, it's the square of the current times the resistance. It's now increasing at an exponential rate. And so it becomes less and less efficient. You have higher losses. And of course, that loss translates into generation of heat. Energy's got to go somewhere. It's either delivered to the load or it generates heat. In a stack tab cell, what you have is you have sheets of electrode. So here, and what we do in a stack tab is then we have the sheets here. We create a sheet, and we have the tab, and we weld that on the end, the corner in here, for one electrode, you know, one polarity, and then on the other side, opposing side, we do that for the other side. And what happens again is the electrons have to travel across the sheet out to the tab, and that's where they exit the cell. And heat has to do the same thing. It's the only way it gets out. If you look at the structure of the cell, it's the same in wound as you saw before. When you wind it up here, the heat has to travel around this coil to get out. It's a welded tab over here. There's a lot of thermal resistance between the wound layers here. Well, the same is true here. When I stack it, I have a lot of thermal resistance, and so the heat still has to get out the welded tabs here, and so you add to it. Same principle applies. If I want greater capacity, I have to increase the square inches of electrode area, get more electrochemical material, and when I do that, the surface area that gets longer, so I have more thermal resistance, I have more electrical resistance, and so I'm increasing the impedance. And the path, I squared R, all the same thing. And so you see that. And again, these are models from NREL. So if you look at the electrode shape here, what happens is you'll see all of the heat actually will elevate here as it exits while the tab's at, and you get this uneven heating on the surface of that sheet. And then as you make them bigger, it just gets, the problems gets worse and worse. Now this here is a battery module. It has a bunch of stacked, this one here has a bunch of stacked pouch cells in here. There's actually external thermal management here trying to cool this battery back down. And that's why you see all the blue down here. But it's not very effective because what happens is the heat, the hot spots up where the welded tabs are at the top, I'm cooling the coolest part of the cell. The hottest part gets less cooling. I can't heat it up, and you'll see that when I show you a module later. I can't cool the hottest part up because this is where it's all welded together. You can't get at that. These are prismatics, again, the hard shelled sort of rectangular cells, and you have the same issue there. Welded tabs are at the top where the terminals are at. It gets hotter as it comes up here, gets to the welded tab. That's where the concentration of energy is at. It's cooler at the bottom. It's more difficult to heat the top because I have all these electrical connections up here that'll short out if I try and put any thermal management system up there to drive the cooling. And so it's not particularly efficient. And again, I have to increase the area. I do that. I have I square R comes into play. Now let's compare and contrast that to how a roll ribbon cell is made. So what roll ribbon cell does, what we do is we actually take the electrode and we make thin strips or ribbons, where the name came from, and we roll it. So it's like a cylindrical cell, except the aspect ratio is very squatty. And to kind of put this in perspective, when you look at it, it's sort of, you think, well, this is sort of like a coin cell. I'll hold one up here. You see, this is the smallest one that we make. So it's the world's largest coin cell. This will run your watch for a very long time. This is the next size up we have there. It's even bigger. And this is the biggest standard cell we make today, although we can make these in any geometry. So these just happen to be standards, that sizes that we're making them in now, because they're convenient for what our customers are interested in at the moment. And the way those cells are put together, so if you look at it, we take a pan here, we have a seal here that insulates between the two pans. So we have two pans. Again, we cut a narrow ribbon of electrode, anode and cathode, and we interleave those together and we wind them up into this roll, and we expose the edges of that electrode here, and we wind that up into that large pellet you see, and then the edge of this comes in contact with the two pans, one on one side and one on the other. We put them together and we put it under pressure here. So here's one cross section of one that's put together. And so you can see that the cathode electrode edge is in continuous, all that edge of that spiral wind is in contact here. There is no tab in our cell. The tab is all of the edges of the electrode for the cathode and for the anode. We have a seal here, this plastic seal here, insulates between the two so that the anode and cathode don't short together. And we press that electrode roll between those two pans, and then we crimp seal this to put it all together. What you see in the structure then is our electrode is this narrow ribbon that's rolled up, hence the term roll ribbon of electrode. And in our model, what happens is all the current doesn't have to run this long stretch of the electrode ribbon that we've created. It goes from where it generates on the ribbon to the nearest edge, comes in contact with the pan, and leaves. So we have a very short path for thermal and electrical, and that reduces the impedance of the cell. So we have less I squared R losses. It decreases the thermal resistance because now we have metal, all the heat's generated on the working surface, the sheet, the electrode, and it connects directly to the pan, which is the outside world, and then we go away. Now, if you want a higher capacity roll ribbon cell, you need more electrode, just like everybody does, more square inches. So what happens is you have a longer ribbon, just like you did with the wound cell. But the difference is we don't have the tab at the end. As we extend the ribbon length, we're extending effectively more tab because we are continuously tabbed along the entire edge of the electrode here. And so as you're adding more electrode, you're adding more surface area to get current and to get thermal energy out of the cell so you can draw the heat out. Now, the way we put that together, you look at this diagram here, so we have the electrode foils here, And you'll notice one of them comes in contact with one pan, the anode pan, the other one comes in contact with the cathode pan. And then there's a separator, what we call a Z-fold, in between the two, so that the electrodes don't short out. There's a separator in the other cells too, but they rely on the tab to get it out. Our tab is the edge. And so we counterpoise these with a Z-fold. The Z-fold ensures that the anode and cathode edges never touch the opposing pan. And so we wind this up in that Z-fold. So you have anode, cathode separator, and electrolytes, what goes between, that's what the lithium ions transport between anode and cathode when you charge and discharge. And so you can see electrode roll, the two pans pressed together, and that's what we saw in the other diagram. And here's the thermal model for what you get for that. So what you see is now you have very cool, all the heat, the total heat that's generated from the work of the cell, based on whatever your loads are, that heat is uniformly distributed across the entire surface of the cell, and therefore the entire surface of the electrode and the pans, both anode and cathode. That ensures you have the least amount of temperature rise because you distribute, and you have the lowest thermal resistance, so the heat exits the cell more quickly. So here's the test results comparing. So what we did in this thing here, we actually did this for the military, had to do with some directed energy weapons. So we took a wound prismatic cell, a couple of them here to get a statistical area, and then we produced a roll ribbon cell. We made the cells identical electrochemical formulations. So these are the exact same electrodes. They were made on the same line, same machine, same time. One cell was wound as a prismatic, and the other one was wound as a rolled ribbon cell. And then we put them through the same torturous test that you can imagine exists for a directed energy weapon, high rate discharge. And what you see is that the DCIR for the rolled ribbon cell reduced, you can see the DCIR here, we reduced the impedance by 50 to 65%, depending upon which one of these you want to use. The ACZ was reduced by 75%, and the high rate temperature rise was reduced. That's not shown in the chart here, but basically the rolled ribbon cell was 23.5 degrees cooler under the exact same load, the same working profile. Basically, it rose by about 10 degrees C, and the wound prismatic cell rose by about 33.5 degrees C, which actually took it into decomposition zone. Again, this is a high stress test. You can see this in thermal images. Here we did thermography, infrared thermography on cells, and you can see how that works. Cylindricals actually have the worst thermal properties, not surprising. And so you can see they have all this heat, and the heat actually migrates. The tab comes out and attaches to the end of the cylindrical. So all the heat you see in the can actually coming from this thermography is the heat that traveled up that little strip, the tab, to the terminal, the tip at each end of the cell. And then the heat traveled from the cap on here back over the can. The temperature inside the can is actually 20 degrees C higher than the surface of that cell. And that's true for all three of the conventional cells. If you look what a pouch cell does, again, same thing. You see really high here at the terminals, very cool at the bottom because all the current started here, very little current flow. Current flow increases it across the sheet as you get to the top here, and then the terminals, and it's all concentrated. Uneven gradients, the cell wears unevenly, and the results are predictable. Here's a prismatic, again, the same thing. And if you look at the temperature inside, it's much higher than the surface temperature. And you have the same issue here with the prismatic. The prismatic actually masks some of this effort here because of the metal can here. So it does a diffusion, but the temperature inside that can, again, is 20 degrees C hotter. Okay, and then you take the roll ribbon here, and you can see it runs very, very cool the entire time. Uniform distribution of heat. So you're looking at this thing again in the thermography. Runs very, very cool compared to the others. Now nobody, for the most part, nobody uses cells. Very, very few. Your cell phones are sort of an exception. They tend to be single cell devices. Most appliances like your laptops and things, they use multiple cells in series to achieve a voltage. So it's all about how do I build a battery? A collection of cells equals a battery, because that's what you actually build into your product. When I take and convert cylindrical cells into a battery module, which is the way people actually consume them, it creates a whole new set of other challenges that you have. So you saw cylindrical cells have very poor thermal properties. How do I turn cylindrical cells, groups of them, into battery modules? So I take those and I line these guys up like little soldiers. And then I have plastic end caps to hold them all in place. I weld plates to the tops of all of these guys here. I weld plates to the bottom of each of those cells there to connect them up. And then I connect the monitoring system here up to all of these cells that are in there and put them into some kind of structure here. What happens is, so that you saw how poor the thermal properties of cylinders are, they need a lot of cooling. When you stack up these cells, how do you get cooling to the cylindricals? It's very difficult. Then further, when you create this, you welded this together in a brick. One bad cell, you throw the whole brick away. You cannot replace the cell. I mean, sole purpose of welding. Welding is to fuse things together so that they're inseparable. Take a pouch cells and turn them into a battery module, and a similar sort of thing happens. Now, it's a little easier, and that's a relative term, to apply cooling. So what they do with pouch cells typically, they will run cooling fins between each of the soft pouches, and they do that for two reasons. It provides some nominal amount of cooling. It also armors up the cell, which is a soft pouch, and it's therefore vulnerable to shock and vibration and other things. So they put an aluminum sleeve around that. Well, that adds to weight and mass and size when you put it in there, and it's actually fairly ineffective because there's an air gap. The other thing that happens when you have a pouch cell is you charge and discharge it, lithium cells expand and contract. And so when you have those sheets, you have to have a space gap. Well, that air gap is an insulator, and you can't really put anything against it to get it out. So the heat sink plates provide some nominal amount of cooling, but it's really de minimis. And then they armor the soft pouches. Again, you have to weld all the tabs together up here to turn this into a battery module. As soon as you do that, you can't separate these guys. One bad cell, throw the brick away. And it's these welded bars here that connect all the tabs together that keep you from putting any kind of cooling up at the top here. The cooling has to come from the bottom. And so that's why they use cold plates at the bottom of this guy to connect with these long sleeves. Again, fairly inefficient. And then they bind all that together. So what happens when I do a prismatic? Well, you have really the same sort of thing. I have the metal cans, they're insulated, the electrodes inside, so there's actually a gap in there. They're not very thermally efficient to the case. All the heat and the current goes out the tabs at the top, and you put all the rectangular cells in there, line them up together. If you want to cool it, you put a cold plate on the bottom here. But again, all you're doing is cooling the can, and the can just gets hot from the heat that starts from the terminal because it came up the tab and then migrates its way over the can. So very little effect back on the electrode, and the electrode is what is going to degrade under thermal. That's what gets destroyed by the heat. So now let's take a roll ribbon. How do I build a battery out of that? Well, first, you can sort of think of it just like flashlights or anything else that you've done. Take our cells, we don't need to weld them together at all. You just stack up, the roll ribbon cells here, anode to cathode, put a couple end caps on here, a couple of compression rods, you squeeze them together, and that's it. You get a bad cell, you take it apart, remove the cell, put it back. Again, all the heat is up against here, against the surface, and then you just hook this all up together. And if you need to cool it off, you have access to all the edges in here. You can put, if in extreme conditions, you can actually put conductive material between each cell. And there are extreme cases, like in some military applications, where they do that, where they'll put stuff in there and it has direct contact. And so that makes a huge difference. The difference between, well, I'll show you that later, but basically the difference between thermal resistance between going layer to layer and anything that's wound or stacked versus the edge of the foil in contact with the cell can surface is on the order, it's at minimum 20, and it's usually on the order of 100 to 200 times lower. So we have completely unmatched, low thermal resistance. So the thermal properties of rolled ribbon. And again, the harder a cell works, the more heat it's going to generate. And we have low thermal resistance, so we can get the heat out of it. And that makes the cell last longer and allows it to deliver higher power. And then we stack all those up, you end up with a module that looks like this. So in this case here, you have 16 cells stacked up between two end caps. You bolt them, and there's a terminal. We have 48 volt brick here. So how do you make a rolled ribbon cell? How does it differ than you've seen a little bit of how it's put together? Well, at the end of the day, it's really almost the same for any other lithium-ion cell. The electrochemical formulation, electrode manufacturing is identical. We don't do anything different. And in fact, we don't produce the electrodes. We have electrochemical partners, established cell manufacturers that we partner with, and we get the electrodes that they make for their conventional cells today, identical formulations. They make it the same way they make it today, and I'll show you how that's done in a second here. So there's no difference. We get the same electrode they're manufacturing themselves, and in fact, it's more efficient because we get, when we use it, we get it coated end to end, edge to edge, whereas they have to do pattern coating and things to do what they do for cylindrical pouches and prismatics. We then slit the electrode. Our slitting process is a little different because we have the narrow ribbon versus the wider ribbons they use. At the end of the day, we use the same equipment, so it's identical. So the only stuff that's different is really the very back end of the cell production. Our winding process, you saw that Z fold makes us different. So rolled ribbon cell winding is different. And of course, our assembly process is very different what they have. And then because of all of that, our electrode filling is different. And then how we seal it up at the end of the day. So the very back end of the process is different, but everything up to the winding of the cell, identical the way any lithium ion cell is made in any other factory. So how we slit it, this is a slitter just like they use in any other one. It's just when we set up the slitter, we set it up to slit and produce very narrow ribbons. And that's what you see here. All electrodes, you start off, the large roller is actually much larger in diameter. This one here is almost the end. These start off, these are called jumbo rolls. These start off and they'll weigh 300 to 400 pounds a roll. We'll stick it on the slitter here. And again, we wind it up, put the knives to it, and then it slits them up and produces feedstock rolls like you see right here. And that's the feedstock rolls that we use. And we slit the anodes and we slit the cathodes exactly the same way. Standard slitter. In fact, this slitter here we use right now, this is like 40-year-old technology. That's how old that slitter is. So it's nothing earth-shaking about it. It's pretty conventional stuff. This year we had to invent, because roll ribbon has that Z fold, that unique thing. So we've created this roll ribbon electrode roll winder. And so what happens is we take those feedstock rolls that we got from slitting and we load them up here, an anode and a cathode over here. And we load them up on the machine. So we put a winding hub on the arbor. The arbor actually sits right down here. So this is a close-in shot looking at this here. So we put a hub on there, and this builds a web of rolled ribbon in the Z fold here. Z folds the separator, tucks the two electrodes between there, and you can see that here. So here's the anode, there's the cathode, here's the Z fold separator. It keeps the two electrodes separated from each other. And when you look at it, when it's done, it makes sure that this edge sticks out a little bit this way, and that edge sticks out a little bit that way, so that it comes in contact with the two opposing bands. When you get done winding an electrode roll here, you see this. So this is two rolls here. Looking at one side and the other, you can kind of see here. The anode is actually coated on copper, so you can see the color of the copper here. You can see the edge of the copper shows on the one side, and then the other side sticks out the other way. So this is another one flipped upside down. And the cathode is coated, in this case here, this is an LFP cell. It's coated on aluminum. And so you can see the edge of the aluminum cell on the other side. I can see it a little better here. So we have a mirror down below this. And so here's an electrode roll that was wound on the winder. And so you can see the copper side, and then you can see the aluminum side, anode and cathode. So we take that electrode roll and we drop it in the pan here between the two pans with a seal in between. And we put that under pressure, and then we crimp seal it. And so then you see, as you can see here on the edge, crimp seal along the edge there. So when you're done, you end up, again, these are the 3 standard sizes that we're producing right now in LFP. So those 3, and which are the 3 cells I showed you earlier. This one here is actually a 13615. LFP makes it 3.2 volts, and this one here is a 15 ampere hour capacity. This one here is a 16515. Ooh, there's a typo there. That's a 16528. This is a 16515, 3.2 volts because it's LFP. And this one here is 22 ampere hours. The last one here, the tallest one, is a 165 by, and this is a typo here, that's 28 millimeters. 3.2 volts again because it's LFP. This cell here, the biggest one, which is here, that one is 45 ampere hours. Again, the chemistry and other factors, electrochemical formulations, it makes some of these, make the voltages change and capacities change. But roll ribbon's all about the package. We can take any electrochemistry, stick it in a can, and it'll perform better in a roll ribbon package. When you take those cells then, you put them into batteries. These are some standard battery configurations that we're working with for our prospective customers, ones we're working with right now. So what you see here, these 3 here, or two battery modules here, actually are 48 volt batteries, and they're using the 165 28 cells. So 165 millimeters in diameter and 28 millimeters in height for each cell. And there's actually 2 columns of 16. So this battery module here is 4.5 kilowatt hours at 48 volts. This single column configuration is 2.25 kilowatt hours, 16 cells. Give you an idea of the scale here. So this is in total, end to end, from the very end to the very end. This is less than 18 inches here. And this here is about, be about 12 inches going that way. This one here will be about 6 inches, again, by less than 18 inches that way. This one here, these 2 cells here, or 2 battery modules here, this one here is a 16515. And there's 16 cells in there, so it's 48 volts in LFP. And that one's 1,000 watt hours. And this one here, you'd be looking at, it would be about a little over about 11 inches for a kilowatt hour there. The other one here, again, it'd be about 11 inches. This one here is 136 15 cells, so 136 in diameter, and then 15 millimeters in height per cell, and 16 cells, so it's 48 volts. And that one is 720 watt hours for that battery. So when you look at roll ribbon, kind of the key takeaways about all of that. So the technical issues are cell package designs are not all the same. The internal temperature is what really matters. Again, you gotta keep your eye on the ball. It doesn't matter what the external package is, but if the external package is hot, the inside's always hotter. In fact, temperature gradient inside to outside on a roll ribbon cell is less than 5 degrees C. A typical cylindrical pouch or prismatic will be 20 plus degrees C, difference between inside and the outside. Low thermal resistance between the cell electrodes and a casing is the key. That's what we do. By making that edge of the electrode in contact with the actual external surface cell fan, which is low thermal resistance, I can extract heat very, very quickly. Cells establish the foundation, so they set your upper limit of performance. If you got a bad cell, everything you do after that, when you turn it into a battery, it's going to make it worse. Batteries never make a cell better; they only make it worse. So you want to start with the best foundation you can get. Conventional cells have poor power capability, again, impedance and thermal issues, high thermal resistance, high impedance, and they don't scale up. It gets worse the more you scale. They have poor thermal properties, and it's very difficult to extract the heat because you're limited. You can only get it out of that thin strip, that tab. It's the only way you're going to get the heat and the electrons out. So they don't scale up. Higher power and high capacity, you're going to get poorer performance. So it's a given. Physics tells you it's going to happen. So what roll ribbon does, gives you better power capabilities. It has unparalleled thermal performance, 50 to 200x, better than any conventional cell. And it scales up. Does it make them bigger in capacity or drive the power rate up? Be able to consume or charge and discharge faster? It scales. So if you have better cells, you're going to end up with better batteries. And with that, open it up if anybody's got any questions about it. There's one other thing. Let's see. Well, yeah, as there. Yeah, I guess wouldn't matter. Okay. Any questions I can answer for anybody?
Okay, there's a couple of questions online here. I'll get to those first, and then anybody else can ask them live. So Richard Evelyn asked, is there any problem with high current through the similar metals like copper or steel at the ends of the stack?
I mean, you can potentially have, but we don't really have that. So part of it is, is picking the materials we use. So we do a number of things, use other supplemental things. One of the things we do, for example, though, is that the copper and aluminum generally works pretty well. We don't have much of a dissimilar problem. There's a paste you can use if somebody feels they have it because they have high moisture or other corrosive elements there. But we actually have, so one side, we actually have nickel-clad steel, and on the other side, it's pure aluminum. And we found that those metals against the copper end plates of the stacks work well. We've not had any galvanic corrosion occurring there because they tend to be relatively compatible potentials.
Okay. Let's see, there's a couple of other ones. How does the connection between the road electrode and the top bottom of the can ensure low resistance?
So go back here. Let's see. Let's help a little. Oop, there we go. So we ensure low resistance. So basically you have the edge of the metal here. So it's metal to metal when you do that. And we do it under pressure. And then you have this massive amount of surface. So the entire edge of this electrode, this spiral wind that you see here, that entire edge is in contact with one band. And the opposing guy has a spiral wind that comes out the other side of the Z-fold. And it's in contact with that. And then we put this under pressure. And so that gives us a very low impedance between there.
Okay.
And like I say, you see it in the test results. It comes out in the DCIR. DCIR is actually measurement of two components. And remember I said, so here's a test, identical electrodes. So we use exactly the same. So the electrochemistry is behaving the same, no difference. They're cut from the same lot, made from the same roll. So you have two parts to DCIR. You have electrochemical resistance, and then you have the structural resistance, which is the metal contact. So you can see from here, the only difference roll ribbon is doing is structurally. It's not changing the electrochemical, right? That's given. Because they both have the same. There's no difference. And so the structural impedance here is much lower with roll ribbon by having that massive edge in continuous contact with the entire band.
Okay, another question. What determines the diameter of the row of ribbon, I guess?
What do you need?
Like,
So we can, no, I say that factually. I mean, it sounds sort of good, but it's not. So the point is, the technology is not limited to a specific size. So I pointed out, we have a standard 6, 15. We came up with some standard sizes because you have to pull something, but the technology is not limited to that. And with our EChem partners, some of them have different geometries they need to make the batteries fit into certain places and applications they want. But until somebody has the application, it doesn't matter. I can't tool, but I don't know what you need. I can tool. I can change this diameter. Our winder can wind anywhere from 100 millimeters in diameter to 200 millimeters in diameter. And that's just the limitation of our winder and what we feel are reasonable buildup tolerances. So we can go anywhere in between there. There's nothing to say what that is other than what do you need? That's what geometry do you need. Same thing with height. We pick 15 and we pick 28. We have one of our partners wants a 40 millimeter eye. So not 28, not 15, he wants 40 millimeter eye. So that's fine. That's what he needs. And no problem. Technology does it. So it doesn't matter to us.
so to add to that, would there be some, there may or may not be, but would there be some concern about reliability versus the geometry? You know, like the bigger it is, probably, obviously, you have a higher chance of failure of some sort, right?
Yeah, I mean, you can have yield issues. There's a couple of things that happen to you as a practical matter. It's not limited by science, it's limited by the practicalities of it. So the more square inches, if you think of like semiconductors, most people are aware, you know, so you make a wafer, right? And you end up with a yield, and a part of that yield is you have so many defects per square centimeter on the wafer, and so that affects your yield, right? And so it's the same thing with an electrode, right? You can have so many defects per square centimeter. So the more material you put into a cell at a given defect rate for creating the electrode that goes into that cell, you have some increase statistically in the failure rate that you'll have in the cell. Yeah, so like any manufacturing problem, that's something that exists. But if I double the capacity of the cell, I've only halved my yield problem based on the defect now. So it's not huge if what I really what everybody wants, right? You want 4 or 5 nines, you know, at least 3 nines, right? So if you double it, you're talking about a couple tenths of a percent. It's not a big deal. Then the second problem you run into is you get buildup tolerances. So like I said, we had to design a winder, and you know, everybody ideally we like to say everything goes DC to light, right? Well, sooner or later you got to say the feedstock roll can't be bigger than the room. So you got to fix that. So what we did is we did an analysis. Certain tolerances build up, they don't scale well. And so we found that after you get a roll diameter above 200 millimeters, it makes the parts increasingly more expensive to make because you have to control the component tolerances when you manufacture the piece parts that go into it more closely. So it just makes them a little more costly because I can only be 100 micron long, whether it's at 150 millimeter diameter or whether it's 200. If I have a part that has to be within 100 micron, well, then it doesn't scale well.
Okay. There are some business type questions. Let me try to get to the technical type questions first, and then we'll go to those. Are your electrodes a powder coating fused to the metal substrate or some other formulation?
Yeah, they're fused. Again, the electrodes are made exactly the same way they're made today. So for those not familiar, what they do when you make an electrode, lithium-ion electrode, you know, for lithium-ion cells, they take the active ingredient, whatever it is, lithium iron phosphate or lithium cobalt oxide or whatever it is, And they create a slurry out of that, which usually includes, first it's got binder in it, which is what binds it all together and sticks it to the foil. And then they coat it on there as a slurry, as a certain viscosity when you apply it. And then they coat it onto the foil, and then it goes through a baking process and a solvent, and then they put solvent in there, which creates the slurry. And then they extract the solvent through the drying process. And so that's how the material gets coated or stuck, you know, sort of pasted to the foil. Then the foil goes through a calendaring process. So you have a certain coat weight you put on there, and then they call it press density. And you go back and calendar it to increase the volumetric density of the material without adversely affecting the morphology.
Okay.
But that's standard process. You do that no matter what kind of, whether you have a cylindrical, pouch, prismatic.
I think we lost that last few seconds of Joel's audio.
Oh, okay. Well, I was just saying it doesn't. Yeah. So all of those things I just explained, that's true for all lithium-ion electrodes. It doesn't matter what kind of package you put it in, whether it's cylindrical, pouch, prismatic, or roll ribbon. You make the electrodes in the same way. So you create a slurry, you put it on there, and the slurry has binder and solvents in it, and then you go through a drying process. And in that process, you extract the solvents and bake it onto the foil, and then you calendar it to achieve your, coat weight and press density without adversely affecting your morphology.
All right, so we have a series of questions about that's kind of related. Let me see if I can ask them together. Have you built a new factory, and are these batteries used by any automakers yet?
No. Okay. So where we're the state of the business. So where we're at right now, the only place roll ribbon cells are made are here in Austin. We have a pilot line. We're not generally shipping cells. We're working with certain partners right now. Next quarter. We expect to start shipping generally to people who are interested outside of partners that we're working with right now. So we'll start shipping cells from there. That's the pilot line. Eventually then, and we secured land already across Highway 290 from where we're at to scale up the factory when we're ready to scale up for high volume. So it'll be manufactured here in Austin.
Okay, so the next questions are kind of related to automotive. So how does it compare? How does your roll ribbon battery or cells compare in size and weight to Tesla's battery, if you are familiar with those? And other than the 52 millimeter versus, how does this compare with the new Tesla tablets 4680 cell? I'm not familiar with that. Are you familiar with what that is?
Yeah, that should be tablets, not tablets.
Okay, sorry.
Yeah. So Tesla has filed a patent disclosure. They've not actually produced anything from those patent disclosure for a tablet cell. They're trying to do some of the same things that roll ribbon is doing. They've not built it yet. Their patent hasn't been granted yet. Their patent may run afoul of some of our patent claims. We'll see. We have a number of patents. But independent of that, they're trying to solve some of the same things we're doing. If you read their patent disclosure, and we've talked to some people involved with that. They actually started that with somebody we were working with at the time, a supercat company they acquired. And but there are some issues they haven't figured out how to solve yet. They can't realize what they're trying to do yet. But that's where they're headed for a lot of the same reasons. They recognize they got thermal issues. They have a different geometry. They're keeping their cylindrical aspect and trying to So they're trying to keep it to look like a cylindrical. They're trying to give it the tab, but they actually only get rid of the tab on one end of the cell.
So with respect
We'll have
to
to see what happens. I don't know. I'm not worried about it.
okay, on thermal issue, are there some kind of failure mode or any kind of failure mode that might lead to runaway or thermal runaway?
Yeah, well, yeah, so there's several things. We will do better in thermal runaway for any given electrochemistry. We will do better because our package design allows you to extract heat faster than anybody else. What drives thermal runaway is that heat builds up until basically you reach the runaway point, and then it's like an avalanche. The biggest component of thermal runaway, the starting place that you have, the baseline that you work from, has more to do with the safety of the electrochemistry than it does, then you get into the thermal properties. And like I say, our thermal properties, our thermal resistance is so low, you can get the heat out faster. So it makes it harder for the cell to escalate the temperature. But at the end of the day, if you put lithium cobalt oxide, for example, in a roll ribbon cell and abuse it in whatever way you have to cause it to trigger a thermal runaway, which you can do, you may have to abuse it more than you would with a different cell type, but you can still drive it to the point of abuse where it will go into thermal runaway. We'll have thermal runaway too. It's just it'll be harder to do that because it's harder to elevate the temperature to the point where it crosses over. I don't know if you know what drives thermal runaway, but basically the thermal runaway in cells has to do with the volatility. The principal thing is that the solvent they use, the organic, it's very flammable and it burns very hot. And the problem is certain of the electrochemistries that you use, quickly, they have different points where they release their oxygen. And so what creates the thermal runaway is that if you trigger an event and it reaches a certain temperature, the separators all melt at about 125 degrees C. And so if you elevate the temperature of the cell above 100, internally above 125 degrees C, or if you get a fault, which will cause it to locally do that, like a dendrite growth or something, some defect in the cell, cause it to heat up, then the separator, which is the insulating material between the anode and cathode, will melt down. And when you do that, all the energy that's stored in that cell is now directed to that short and begins to rapidly increase the temperature there to the point where you will cause the electrolyte to catch fire. When the electrolyte begins to burn, breaks out, it burns very hot, and then it rapidly raises the temperature of the whole cell. Different materials, like LCO, has a very low point where it'll release its oxygen molecule. And so what happens is after you reach that temperature, and like LCO, it's like 250 degrees C. So when you get about 250 degrees C, LCO gives off its oxygen molecule. So now there's no way to put the fire out, right? It's got all the oxygen it needs, it's got all the electrolyte to burn that it needs. So it's going to burn until it burns everything up. If you use like LFP, for example, LFP is much lower energy density, so it's harder to heat that mass up to where it does it. And LFP, you have to get well in excess of 500 degrees C before it'll give up its oxygen molecule. So it's very difficult to cause it to run away. So chemistry matters, and then what are your failure modes matter. At the end of the day, if you can keep it cool, you make it harder for it to hit that trigger point. And that's what we do. We keep the cell cool. But we don't sell roll ribbon on the basis that it's an order of magnitude safer, for example. That's really not. If you really want an order of magnitude increase in safety, pick a different chemistry. Don't pick a volatile chemistry, because you can do all the things you want, but at the end of the day, it's like you look at like Teslas. Go to YouTube and see a Tesla burning in a stoplight. You never see one that just sort of partially burns. They talk about all their firewalls and that. Go find a YouTube video somewhere where the car isn't total, didn't eat everything. They always do. The runaway is complete. It doesn't matter about their firewalls. And most of their original cells were LCO, then they went to NCA, which is still pretty volatile. And, you know, so it turns more on the safety of the chemistry than it does something else.
All right. Okay, here's I'm on chemistry again. How much does it improve the charge and discharge rate of the lithium ion chemistry?
Yeah, so it's one of those things. Everything about electrochemistry, as with a lot of other things that most people don't know about, it's a statistical problem. So when you talk about what something does, you talk about it in a context of what are your requirements and what are your needs. The thermal properties we have, we keep the cell cooler. It turns out the cells last longer when they stay cooler, even when you don't abuse them. they're gonna last longer if you don't abuse them, and the cooler you keep them, the better they're gonna behave. So what we found, for example, is, and I can tell you firsthand. So we have an EChem partner. He uses an electrode to make cylindrical pouches and prismatics. We get about 25% more, 25 to 35% more cycle life, makes the battery last longer at the same discharge rates he designed for his other cells. That's because we keep it cooler. Identical electrochemistry, right? We're using the same electrodes. There's nothing different about it. So it's just kind of cooler. Well, that's a statistical problem, right? If you didn't need the cycle life, then it wouldn't matter. It doesn't improve it at calendar life level, but cycle life, keep it cooler, it's going to run longer. Maybe cycle life doesn't matter to you. Maybe power delivery matters more. Well, it turns out, give you another example we did with the Navy for a rail gun. So they took somebody else's cylindrical cells and they were having trouble. That's part of how we got involved with it. And they were in trouble with their cells. Their cells wouldn't last very long and they couldn't get the power delivery they wanted out of it. So they ran a test. We took the other guy's cells and they said, okay, well, here's what we need, even though the cell won't deliver it. Let's do it and let's see how long it lasts. You know, how long can we put these batteries in the ship, send it out to sea, even if we use it, maybe we don't need it to last as many shots before we have to replace it. So they did that. What happened when they put in the abusive condition is the cylindrical cells that they were using were designed for power. They lasted 50 to 75 cycles. Then they subjected our electrochemistry, which is designed for much lower rate, same abusive condition as was the other cell, and they ran rows of ribbon cells. So under our normal specs, we were 2,000 plus cycles for it, just as they were. The cylindrical cells were 2,000 plus cycles. When they subjected to the abusive condition, cylindrical cells died in 50 to 75 cycles. We lasted 500 cycles. So we lasted a lot longer. Only difference, thermal.
Okay, so sounds like you are. I think Tesla claimed that their cycle is between 1,000 to 1,500. So it sounds like you are an improvement over there.
Yeah,
okay.
they're not even at that 1,000, 1,500 right now.
That's what they claim in their
Most of their stuff is
marketing.
1,000 right now.
Okay.
Their goal is to hit 1,500. But again, that's the chemistry they're using. If you're using NCA, which is what they're using, it's very difficult to get over 2,000 on NCA. It doesn't cycle that well. LFP cycles better. LTO cycles really good. Very expensive, low energy density.
Okay, here's a business question. So, are you a public or private company? Do you have a stock, and can you comment on some of your customers?
I can't talk about customers. I mean, I've mentioned some people we've been working with, but I can't really speak to customers. We're privately held.
Okay. Yeah. Any other questions here? Do you know what cell types aspect ratios are being used by Rivian and GM in their new electric vehicles? So this is automotive related again.
Yeah, the automotive guys are using all kinds of different stuff. I'm on a couple of committees. Some of which I've got access to information I can't talk about, but they're not all using one type of cell. Like Tesla's been gravitating toward the, you know, they've been gravitating toward that 800 cell, the 3800. That's sort of their new thing, and that's before they put in their tabless design, which they're looking for space. They're the only ones who really are aggressively in that. Most of the other guys are running with pouch or prismatic, not so many of them.
So here's kind of a technical question too. Tesla determined that the most optimum shape is 4680, whereas you claim, or Roll Ribbon claim, that it is the disc shape of a wider and thinner size. So are you just patenting a different shape?
Well, no, it's not the shape. I mean, it's how it's put together. Our patent covers the Z-folded structure, which, if you look at the patent disclosure that Tesla has made, it's not clear how you would actually make their cell work, but I don't want to go there. It's really unimportant. But the point is, it's not just you know an aspect ratio that defines full ribbon. It's the fact that you have the edge of the electrode in contact with the pan, Z-fold, forces, separation, press it, do various things. All of those things that make a difference. That's what the patentable claims are. They're not. It's not just because we happen to be 136 or 165, or because we're wider than we are tall.
What is the operating temperature of your cells, of the ribbon cells?
It's the same as anybody else. That's on the electrochemistry. Again, we're about package electrochemistry. Give us another electrochemistry. The way we actually, arranged, the way we got connected with our echem partners is we started off and, told them about what we were doing, established cell manufacturers, and they said, well, that's interesting. We said, hey, let's have a bake-off. Send me electrodes and your commercial cells, bake it, and let's have a bake-off and see who does better. So they'd send us their electrodes. We make it a roll ribbon equivalent to a cell they were already in volume production with. And they all discovered that the roll ribbon cell always outperformed their cell. So that's kind of how we got into it.
Okay. Glenn Jenkins commented that GM uses pouch type cells. So that's just a comment for everyone.
Yep.
And okay, Bertram asked any discussion about Ford. Do you know anything about what Ford's doing?
They've actually experimented with various different types, but they've done both pouch and prismatics.
Okay. Do you know anything about the new lithium glass cells from Dr. Goodenough at UT Austin?
No, I do not.
Okay, it's lithium.
Oh, I mean, the only thing I know about is what he's publicly.
Okay. All right, I think that's all the questions I see right now. If I missed some, go ahead and just unmute yourself and ask it live right now if you like. Anyone? What is the NCA chemistry?
That's nickel, cobalt, aluminum. That's currently what Tesla's using. They're the principal user of NCA.
Oh, okay. That's Tesla's technology. Okay.
It's not Tesla's technology, but that's what they're using.
Yours they're using. Okay.
Yeah.
All right. Anybody else got questions?
Well, it's 7:34, so let's give the Joe a good hand. And then let's
Right.
close the meeting tonight. Any other questions?
Anything else? Okay, I'll stop the share then.
Yeah. All right, thank you.
Thank you
Thank
for
you.
the
Nice
presentation.
presentation.
Very good, Joel.
Yep,
Thank you.
my pleasure.
Thanks, everybody.
Thank you. Thank you very much.
Thanks everyone for
Bye.
attending. Good evening.
Okay,
All right, so we'll see you next month. Okay, bye.
Good night.
all right.